Hey guys, what's up? Welcome back. We are in triple integrals, and we talked about triple integrals last time. We introduced them. We did rectangular coordinates. Today we're going to do kind of similar what we did in double integrals. We're going to change to a new coordinate system. So today we're going to do triple integrals in cylindrical coordinates, and that's section 15.7 in the Stewart Calculus book. So triple integrals in cylindrical coordinates. So triple integrals in cylindrical coordinates. So first of all, what we have to do is we have to figure out, what are cylindrical coordinates. So let's kind of introduce the idea of cylindrical coordinates and then talk about doing triple integrals in cylindrical coordinates. So what are cylindrical coordinates? So what are cylindrical coordinates? So that's kind of the question we want to answer first. Well, the name kind of suggests that cylinders are involved somehow. So let's just kind of recap what we've done so far with coordinate systems. So recall, let's say the 2D case. So in the 2D case, we had Cartesian coordinates, or rectangular coordinates, and that meant every point in R2 is somewhere on a rectangle. So that's what rectangular coordinates essentially mean, right? That's the heart of rectangular coordinates. We could say every point in two-dimensional space is somewhere on a rectangle. And so whenever we talk about locating points in space, we identify an x and a y coordinate. Well, that tells us which rectangle it's on. We also had 2D coordinates, polar coordinates. So polar coordinates, that said every point in R2 is somewhere on a circle. So it's just a different way to describe the space. You use two different coordinates. You use r and theta. R being the distance from the origin, theta being the angle off the polar axis, or you could say off the positive x-axis if you wanted. But yeah, it's just a different way to describe the two-dimensional space, or to locate the points in the two-dimensional space. Okay, so that's 2D. In 3D, we have rectangular coordinates again. And again, every point in R3 now, because it's three-dimensional, in R3 is somewhere on a rectangular solid. So somewhere on a box, basically. So the intersections of all the different planes create, three-dimensional boxes. And every point in three-dimensional space is somewhere on a box. Okay? So you specify an x, y, and z coordinate. That tells you where to go, or where it is on the box, on some box. It could be the corner of a box when you intersect all the coordinate planes. Or when you intersect all the planes, x equals a constant, y equals a constant, z equals a constant. You create a bunch of boxes that way. So today, what we're going to do is talk about, call it part B, cylindrical coordinates. Cylindrical coordinates. And that means every point in R3 three-dimensional space is somewhere on a cylinder. So somewhere on a cylinder. So it's very similar to polar coordinates in that there's like a circularness to the coordinate system, but there's also a vertical component on a circular cylinder. So now we basically have polar coordinates with a three-dimensional aspect. So if we draw three-dimensional space, you know, in the X, Y, and Z setup, it looks like this. And we might have a point out here. You know, this might be our point. And that point could be projected down into the XY plane, you know, like this. And what we could say is that the X, Y, and Z coordinates are actually related to these other coordinates, R, theta, Z. So here's R, here's theta, and we already know this one is Z. So it's just a different set of coordinates to describe the location in space. It's the same location, it's just a different set of coordinates describing where it is. And basically, if you rotate theta all the way around, you could say this is on a cylinder. Of radius r. So the point r theta z is on the cylinder of radius r at height z above XY plane. So we'd call this point the point r theta z. So it's very similar to polar coordinates, except there's a three-dimensional aspect to it. There's a z component to this circle, basically. So it's very similar to 2D polar coordinates. Any questions so far about the concept, the idea behind cylindrical coordinates, before we move on? Alright, so now let's relate cylindrical coordinates to Cartesian coordinates in 3 dimensions. So converting or conversions between rectangular and cylindrical. So how are the two coordinate systems related? Well, those r and the theta, they're actually the same r and theta from polar coordinates. So we could say that x is r cosine of theta, y is r sine of theta, z is just z. So if you have the cylindrical coordinates, you can get the Cartesian or rectangular coordinates. Likewise, r is going to be square root of x squared plus y squared. Or you could just say r squared equals x squared plus y squared, same thing. Theta is going to be arctan y over x, and then plus pi as needed, since arctan's range only goes from negative pi over 2 to pi over 2. Or, equivalently, you could say tangent of theta equals y over x. And then z is equal to z still. So if you have the rectangular coordinates, x and y, you can get the cylindrical coordinates r, theta, and z from that. So those are our conversion factors, or our expressions that we're going to substitute in as needed. Probably the three, well, z equals z is kind of trivial, but the three that are like the most important are probably these two here and this one right here. Those are probably the three you're going to use the most when you're doing triple integrals. You're going to substitute these in instead of x, y, and z. You're going to switch them to r cosine theta, r sine theta, or even r squared if you have x squared plus y squared. Z is going to stay z. So before we get to the triple integral stuff, let's look at just a few things conceptually. Think about cylindrical coordinates a little bit more deeply, and then we'll get to the triple integral section. So example, describe the region, and the first one is r equals 4. The second one is theta equals pi over 3 with r greater than 0. I should say describe the regions, since I have two examples here. So solution, we're in three-dimensional space, so we have to keep that in mind. We know what these are in two-dimensional space, but what are they in three-dimensional space? So in 3D cylindrical coordinates, well, r equals 4 is a fixed distance from the z-axis, because that's what r measures, right? The distance from the origin, or the distance in this case from the z-axis. So we have a fixed distance from the z-axis regardless of theta and regardless of z. So if we draw this is part A. So if we draw a set of axes in 3 dimensions and we draw a fixed distance of 4, that's a circle, and then regardless of z as well, we just see an infinite cylinder. So the answer for part A is this is an infinite cylinder wall. Infinite cylinder wall. Infinite circular cylinder. So that's what r equals 4 represents in cylindrical coordinates. Kind of like it represented a circle in 2D polar. Well, now you have a z component, so you can express, or you can stretch that circle up and down the z-axis. So every z value, you're going to see the same circle. So your traces are all circles. R equals 4. Any questions so far? All right, so part B is, let's see, theta equals pi over 3. So let me come over here, part B. Theta equals pi over 3 is a fixed angle off the x-axis regardless or independent of r and z. Of course, r is positive, we said. But let's just draw some axes again and come out to the angle pi over 3, which is like, we'll say right there. Now the r value can change, so it can go this way as far as it wants, but the z value can also change, so it can go up and it could go down as well. So it's actually an infinite vertical plane. So it's an infinite vertical plane at the angle pi over 3. So infinite vertical plane at the angle pi over 3. So conceptually, that's what these represent. So hopefully we got a little bit better feel for cylindrical coordinates and what they do for us and how we work with them and things like that. So any questions before we get to the integration part? All right, so let's look at how this relates to triple integrals. So theorem, if the solid region E is given by, say, z goes between k1 of r theta to k2 of r theta, and r goes from g1 of theta to g2 of theta, and theta goes from a to b. So if those are your bounds, then the triple integral over the solid region E, f of x, y, z dv can be represented in cylindrical coordinates as integral a to b for theta, integral g1 of theta to g2 of theta, integral k1 of r theta to k2 of r theta, f of r theta z, so basically substituting in r and theta such that x is r cosine theta, y is r sine theta, and then the dv is going to become r dz dr d theta. So, question, why is dv equal to r dz dr d theta? This is very similar to what we had for polar coordinates. So the answer is we consider differential changes in each variable. And we get a nice little differential volume that looks something like this. And this little delta R, this little delta Z, this little angle here, delta theta. So this delta volume is going to be the length times the width times the height, approximately, because the changes are so small. It's basically like a rectangular solid, even though I've kind of exaggerated the curvature. It basically would be a rectangular solid, and the length would be delta R, the height would be delta Z, and the width would be the arc length R times delta theta. So this last one is kind of the key. It's an arc length. And here we're saying approximately because it's approximately a rectangular solid. It's approximately a rectangular solid if changes are small enough. So that's why the dV becomes R dz dr d theta. Any questions about the setup for the integral? A lot of times people call this a differential volume element. All right, so now I guess let's just look at some examples if there are no questions. So example, evaluate the triple integral over the solid Q e to the x squared plus y squared dv, where Q is the solid bounded by the cylinder x squared plus y squared equals 9, the xy plane, and the plane z equals 5. So what I like to do first is graph the solid region. So graph the solid region first. It's kind of what I did for triple integrals in Cartesian coordinates. So let's draw the cylinder above the xy plane. And let's try to find the bounds for r, theta, and z. So r, we know, is going this way. And here the cylinder's radius is 3. Z is going from 0 to 5. So r is going from 0 to 3. Z is going from 0 to 5. And theta is going from 0 to 2 pi. So there's no restriction on theta. Theta is going all the way around. So r is going from 0 to 3. Z is going from 0 to 5. And theta is going from 0 to 2 pi. Going all the way around the z-axis. So it says no other restrictions except inside the cylinder, above the xy plane, and below the plane z equals 5. So those are our bounds. So actually integrating over a cylinder in cylindrical coordinates gives constant bounds. So just a note. Integrating over a cylinder in cylindrical coordinates gives constant bounds. So just something to keep in mind. Just like in Cartesian coordinates, integrating over a box gave us constant bounds for x, y, and z. Integrating over a cylinder in cylindrical coordinates gives us constant bounds for r, theta, and z. So now we can go straight to the triple integral. So the integrand, we should change the integrand, f of x, y, z equals e to the x squared plus y squared will turn into f of r theta z which will become e to the r squared. So our integrand is going to change to e to the r squared. So then our integral becomes integral 0 to 2 pi for theta, integral 0 to 3 for r, integral 0 to 5 for z, e to the r squared, and then our dv is r dz dr d theta. And this is constant bounds. It's separable, so actually we can change it to be integral 0 to 2 pi d theta, integral 0 to 3 r e to the r squared dr, integral 0 to 0 to 5 dz. So we know what the first and last integral are going to be. Those are going to be pretty easy. So this is going to become 10 pi integral. How do we do the second integral? So the second integral, we're going to do u equals r squared. du is 2r dr. And if r equals 0, u equals 0. If r equals 3, u equals 9. This can become integral 0 to 9 e to the u du over 2. So that's going to be 5 pi e to the u from 0 to 9, which is 5 pi times e to the 9 minus 1. Any questions? All right, no questions. Let's see. We'll do some more examples here. Just wait another second to see if there are any questions. All right. Another example. Right. Triple integral in cylindrical coordinates. So write the triple integral over q f of x, y, z dv in cylindrical coordinates. So don't actually evaluate anything because I'm not giving you a function f of x, y, z. I just want to leave it f. But I really just want you to find the bounds. So that's really the goal of this problem, is just to find the bounds correctly. And the solid region Q is the set of all triples x, y, z such that square root of x squared plus y squared less than or equal to z less than or equal to square root of 18 minus x squared minus y squared. So that's our solid Q. So the hardest part is going to be trying to figure out what is represented by this region Q, or this set of pairs or triples. So what is the set, or what is the solid region Q? So what is the solid region Q? So the lower bound is z equals square root of x squared plus y squared. We could square both sides and say that's z squared equals x squared plus y squared, and we know that that is a cone. So it's a cone, and once we know that it's a cone, we can look back here and say it's the top half of the cone, since we took the positive square root. So we know the lower bound now is a cone. So if we just draw our axes here, and we look, we've got a cone at the bottom. So we're above that cone right there. So this is the top half of this cone, so don't draw the bottom half. And we know that our z values are going to be larger than this cone. So what is the upper bound? So the upper bound is going to be z equals the square root of 18 minus x squared minus y squared. Again, squaring both sides, we get z squared equals 18 minus x squared minus y squared. Move the x and the y to the left, you actually get x squared plus y squared plus z squared equals 18, and that's a sphere. Centered at the origin with a radius square root of 18. So it's a sphere, but again, looking at what we have here, it's the top half of a sphere, so top half, since we took the positive square root. So it's the z values larger than, or sorry, it's the z values that are going to be less than the sphere. So the sphere, somewhere like right here. So we're going to be in between the sphere and the cone. So z already we're told is ranging from the cone to the sphere. So that's our region of integration. So I'm going to erase the rest of the sphere. It was only the top half anyway, so I should just draw the hemisphere. So that's kind of our region of integration. All right, so if we switch these two to polar coordinates or cylindrical coordinates, in cylindrical coordinates, the lower bound is z equals square root of x squared plus y squared, which is square root of r squared, which is r. So it's just a cone z equals r. So that's the lower bound for z. The upper bound is going to be z equals square root of 18 minus, I'll put in parentheses, x squared plus y squared. Factor out that negative, so square root of 18 minus r squared. So that's the upper bound for z. So far we've got z goes between r and square root of 18 minus r squared. Theta is an easy target because it goes all the way around the z-axis. It didn't say anything like in the first octant or whatever. It just said between these two surfaces. So our bounds for theta already are 0 to 2 pi. But what are our bounds for r? So the question now is, what are the bounds for r? So question, how do we find the bounds for r? Well, the lower bound is going to be the z-axis, so that's going to be 0. But what's the largest value of r? So the largest value of r occurs when these two intersect. So this distance here is the radius where they intersect. So r of intersection. So how do we find where they intersect? Well, we set the two surfaces equal to each other. So the answer is find the intersection. So they intersect when r is equal to square root of 18 minus r squared. So that would be r squared equals 18 minus r squared. Or 2r squared equals 18. Or we could say r squared equals 9. Or r equals 3. So r is actually going to range from 0 to 3. And those are our bounds. And if we set it up as a triple integral now, the integral will be integral 0 to 2 pi, integral 0 to 3, integral r to square root 18 minus r squared. We would change the integrand to f of r theta z, and then r dz dr d theta. And that would be how we rewrite the integral using cylindrical coordinates. Questions? Okay. So look at another example. So let's say another example here. Switch to cylindrical coordinates to evaluate. So switch to cylindrical coordinates. To evaluate. And we have the integral from 0 to 1, integral from negative square root of 1 minus x squared to positive square root of 1 minus x squared, integral x squared plus y squared to 2 minus x squared minus y squared, x squared plus y squared to the 3 halves, dz, dy, dx. So we have this nasty, well, it looks nasty, at least in Cartesian coordinates. It's very unappealing in Cartesian coordinates. But maybe it'll be better if we switch it to cylindrical coordinates. So as always, first you want to graph the region. So first graph the region of integration. So that's kind of the first thing we always want to do, is graph the region of integration so we can switch the bounds to a new coordinate system. So let's look at what the bounds are telling us right now. The bounds are telling us that x is between 0 and 1. And then the y bounds are between negative square root of 1 minus x squared to positive square root of 1 minus x squared. And then z is going from x squared plus y squared to 2 minus x squared minus y squared. So what is this? Well, in the xy direction, we have x greater than 0. So between 0 and 1. So here's 1. If you square both sides of this y inequality, you basically see circles. X minus x, or 1 minus x squared equals y squared. And say see x squared plus y squared equals 1. So it's like a circle, but it's like the right half of a circle because x is greater than 0. So in the xy direction, it's part of a circle. And now let's look in the z direction. So the lower bound for z is z equals x squared plus y squared. And we know that is a paraboloid opening up. So that's a paraboloid opening up. And the lower bound, or sorry, the upper bound in the z direction is z equals 2 minus x squared minus y squared. And that's actually a paraboloid opening down. Paraboloid opening down in the z direction. So if we just look at the z direction, we see a paraboloid opening up like this and a paraboloid opening down like this. And normally we'd say everything in here, but we have some restrictions. It's everything to the right of the or everything in front of the YZ plane. So, but only things in front of the YZ plane, since x is greater than 0. So if we try to graph this, save this. Well, let me try to draw better. Something like that. Something like that. Use a different color. So it's kind of coming only in the x direction. It's not going back. So it's flat against the YZ plane. So that YZ plane is cutting it off in the back. Normally it'd be a nice circular object, but it's only half, the front half of it. So it's kind of the space in between these two paraboloids in front of the YZ plane. Does that make sense? The graph. And we can kind of see where the circle of radius 1 comes from. It's actually where these two intersect, right here. So these, you can show that r squared equals 2 minus r squared intersects at r equals 1. So that's 2r squared equals 2, or r equals 1. So these two paraboloids intersect at a radius of 1 right here. So intersect at a radius of r equals 1. All right, so we've kind of got our bounds. Let's think about the bounds. R is going from 0 to 1. So this is basically R. So R is going to go from 0 to 1. Z is going to go from the bottom paraboloid to the top paraboloid. So that's going to be from r squared right here to 2 minus r squared right here. So r squared less than or equal to z less than or equal to 2 minus r squared, converting those two bounds to cylindrical coordinates. But theta is going from, we'll say, negative pi over 2 to pi over 2. So the bounds for theta, we'll say, are negative pi over 2 to pi over 2. So our integral becomes integral negative pi over 2 to pi over 2. Integral r squared, whoops, do r next, 0 to 1 for r. Integral r squared to 2 minus r squared. Our integrand was x squared plus y squared to the 3 halves, so r squared to the 3 halves. R dz dr d theta. And again, it is a nice, well, I guess it's not quite separable because the z bounds have an r in it, but the d theta can come out front. So I could say that this is going to be equal to integral negative pi over 2 to pi over 2 d theta. Integral 0 to 1. And, whoops, that should be 3 halves. So that's going to be r cubed times r, which is r to the 4, integrating r to the 4, which is like a constant with respect to z, we just get z from r squared to 2 minus r squared dr. So this is going to be pi over 2 plus pi over 2 out front, integral 0 to 1, r to the 4 times, plugging in the bounds, we get 2 minus r squared dr. So this is going to be pi integral 0 to 1, r to the 4 times 2 minus 2r squared dr. Nice polynomial, so pi times two over 5 r to the 5th minus 2 over 7 r to the 7 from 0 to 1. Of course, I distributed the r to the 4 inside the integrand, so we just highlight that here. And then integrated. So this is going to be pi times 2/5 minus 2/7. And this is going to be pi times, see, multiply by 7, we get 14 minus 10 over 35. 4 pi over 35. And that's our answer. Any questions? Okay, good stuff. So next time, I know we had the exam scheduled for today, but it got pushed to Monday. Well, now I'm pushing it to Wednesday. I think you should have gotten an email this morning. So next time we're just going to do spherical coordinates, and that's going to be a little rough. So we'll come back and review that before the next exam, or the third exam. Because I know it's probably not a good time to be learning a lot of new material. So I was hoping the second exam would be Monday, because today's material is actually a little bit of review from polar coordinates, more or less. So I was hoping we could get that exam in, but we're going to have to push it to Wednesday. We don't have to, but I'm going to, because there's a conflict with an engineering exam. So just a heads up. I sent out an email this morning about that, but yeah, we'll do spherical coordinates next time. Exam on Wednesday. Then we'll get into chapter 10 and 13. So go back to 10 for one section and then move on to chapter 13. But what's on the exam Wednesday? The exam's going to be polar coordinates 10-3, and then 14-1 and 2, and then 15-1, 15-2, 15-3, and 15-4. So it's polar coordinates, multivariable functions, double integrals over general regions, double integrals in polar coordinates, and applications of double integrals. So all the triple integral stuff will be on the third exam. So don't worry about triple integrals. But we did cut polar coordinates from the first exam, so we're going to put polar coordinates on the second exam. So yeah. Any questions? All right, I'll hang around for a minute, see if anybody has any questions. If not, have a good weekend. Happy studying. It's going to pay off for sure. You guys keep working hard. Great job so far. See you guys next week. Have a good one.